second talk of this morning. So Paolo Aluffi is going to tell us about CSM classes for matroids.
Okay, thank you. My talk is 10:23. I apologize in advance. I don't know whether I talk for 20 minutes and then be done, or whether I need 1.5 hours.
Questions?
Not only with questions. I need to do something I always do when I teach that this makes well. That's right. So thank you very much for being here, and thanks for the invitation. This is very pleasant conference to be at, and I really like this kind of free-form style of discussions without. And also, I took seriously the idea that we should not just talk about our latest thing. I wanted to, in fact, there will be extreme view of my own contribution to this. I just want to advertise what seems to be happening in the more combinatorial side that has really a counterpart to what people have been thinking about for a long time. And maybe most of you already know this story, which is there with me, but maybe not. I know very, very competent people. If I say matroid, their eyes kind of glaze over. It's a word you've heard for a long time, but you may not be very familiar with it. And my purpose here is to advertise a certain context in which I think there's lots of work to be done. And Jörg already gave a hint of this in his talk. And, yes, that's it. I think it's good news. There are lots of things that need to be done, and it's the beginning of the story. So let me start really with telling you or reminding you of what a matroid is. So, actually, I'm really curious. How many people are somewhat comfortable with this? Yes, of course. I'm glad that not everybody saying yes and no.
There were like 5 equivalent definitions.
Yes, let me give you the one that I understand. So, and let me motivated by the standard example. This is not the definition of matroid. This is something that you are very familiar with and you can contemplate. So I want it to be a vector space. So this is an example, right? It's a little funny to start a definition with an example, but I really think that this is the way to think about this. And take a bunch of vectors in space. In fact, let me give a name to the indices in the 0 to 1. And I encourage you to think about the following. M as in matroid is a set, and a set of linearly independent subsets of this collection. Okay, so everybody can think about this. Take 3 vectors in space. Maybe they are linearly independent, maybe they are coplanar, and then you can just list all the subsets of that set of linear independent subsets. And what you should think about is what axioms does M satisfy? And this could be a quiz. I could ask you to just list 3 things about M, and you will probably come up with this list. Number 1, the empty set is independent. Nope, not a controversial thing. Number 2, if I is independent, then and J is a subset of I, then J is independent. And number 3, which is maybe the cleverest, is suppose you have I and J, and you know that which is larger. I use different letters in my notes. If you have I1 and I2 independent sets, and one is smaller than the other. Then what can you do? Well, you can borrow one of the larger sets and throw it in and get still an independent set. So there exist 2 indices sorry, one index.
Do you mean one is included in the other?
No, just I have 4 vectors here and 5 vectors there, where I can take one of the 5 vectors and that will give me a time such that I1 union I is the okay, so these are reasonably simple-minded things. And what you're looking at this, and here is the definition of matroid. So I could now start the definition. And for the definition, you start with A times Z. So maybe I should write A matroid M on E equals 0 N is a subset. Is a collection of subsets. Of E such that. Alright, so it's really just abstracting the most elementary observations about linear independence. Is there something wrong?
Second is I element of. Sorry.
No, thank you.
Sorry, why the word matroid? This sounds like matrix or something.
Who came up with the word matroid? Whitney or someone like that? I remember that Giancarlo Rota did not like the word matroid. He tried to push combinatorial geometry, which is a nice, and that's occasionally still used, but matroid is taken.
No, it's a popular name.
Also,
But
you
the
can
basic
make,
model is that, no, nothing to do with matrices or anything, no.
no, you can start with the matrix and look at the columns. Then that's a bunch of vectors, and
Yeah,
there are.
You can look at coordinates.
Excuse me?
You can look at the Brucker coordinates. Ky
Right,
and
right.
matrix. And look at the Brucker coordinates for that one.
Yeah, without thinking about that. Yeah, you can check the independence or a bunch of vectors. Yes, Richard mentioned that there's many different definitions. This is one of them. I think it's actually one. There are different points of view. I'll come to that. If you want a loaded question, is it true that everything satisfying this can be realized like that? Yeah. Consider, when you think of such an example that does not arise in this. That's a fair question, and I'll come back to it.
But also the question can be asked, what field? So the answer is different for different
let
fields.
me, maybe as terminology, you say that M is realizable. I will use either realizable or representable. I think, as far as I can tell, they are synonyms in this story. Representable over a field K. It can be realized by a collection of vectors in a K-dimensional, a K vector space. So the question would be, are all matroids realizable? Over some field? There's more terminology in it. It's regular, it can be realized over every field. Okay. I should not erase that until I'm done with those.
I think that was the motivation of geometers 2,000 years ago,
2000 years ago?
at least.
People were doing matroids then. That's impressive, no?
One of your pictures is about that.
Probably.
Yeah.
So let me raise a little bit of terminology. So there's a funny thing, a loop. We use this word exactly twice. Once is here on M if I is not in any independent set. That's one time I need to use this word. The second time is here. A matroid is loopless if you don't have such things. I lied. I need a third time. All matroids will be loopless. Forget about this if you want. What is this generalizing? It's generalizing requirement that the zero vector should not be. You don't want to have it. Loopless generalizes this. Because the zero vector cannot be part of any independent set. It is a convenient assumption that is. More importantly, more important names are rank of a subset in E is the max size of an independent set containedness. Of course, you see what this is, right? By the way, I didn't mention that out of these, this is all you need to know, for example, to know that you have bases on the same cardinality, that all maximal linear independent sets will have the same number of elements. And what this is trying to make you think of is the dimension of the span of the set of vectors. Flats. Those are the maximal subsets of a given rank. So what are you thinking here? You have a bunch of vectors. I mean, all my intuition comes from the realizable case, so I always refer back to the realizable case. Here we are looking at all the vectors in the span of some of the vectors. You need a bunch of vectors, see what they span, and then take all the vectors in your collection that are in that span. That's what a flat is. Flats form a lattice. And that's what those pictures are going. Yeah, so as Richard mentioned, there's many different alternative equivalent definitions for matroids. You can use, you can just give the correction of flats and then reconstruct what it means for HUD. You can give the rank function of subsets of E and reconstruct what it means. So each of these has a corresponding definition if you want. Just choose one of them. Anyway, back to this question. All matroids realizable. Can you think of other ways to make matroids? Let me propose one that is I find very cute and also will be relevant. Relevant, I'm not sure. Too relevant, but it will be a good motivation for another notion. Other examples. You can make a matroid out of a graph. So start with a graph. I like example, so here's my graph. Let me give numbers to the edges. This is going to be my E set. I want to get a matroid on this set E. So this I have to tell you what the independent sets are, and they are going to be the I's. Such that the collection of edges in I does not form a cycle, contains no cycle. I'll just say I does not contain. Okay, so you can prove that this is a matroid, it satisfies the same actions that I very carelessly used. That's more difficult, matroid. And if you want to look at this example, it gets fairly long already for small examples, but if you want to start writing these things, now 0 by itself has no cycles, 1, 2, 3, 4, and 0, 1, 0, 2, and so on. You can just list all the guys that do not run cycles. So for example, 0, 1, 2 will not be in write down the choice. What are the bases? I should have added it to terminology. The bases are not the bases. Is a maximal set in M, so the maximal linearly independent set. That's what you're thinking. The bases are not too bad here, so we just write them out. The basis would be the same as what people call a spanning tree, right? A maximal spanning tree. That's the terminology. Correct me if I'm wrong. The largest trees you can put in here, and just some things I don't want to do in real time, so then just copy my list. This will come back at some point. I am organized as I think I am. There we go. It is at least all possible spanning trees. 0, 1, 3. 0, 1, 3, that's this spanning tree. 0 to 4, it's 0 to 4, and so on. Okay, those are all the largest sets, all independent sets. Over here this is the lattice of flats. I should not write here for a reason. In this matroid, so for the drive I have over there. Okay, are you going to trust me on this? I suppose. All right, so you can see now I'm drawing the graph in not this way. 0 is connected with 0, 1, 0, 2, 0, 1, 2, 0, 3, 0, 4, and so on. One reason why I want to have this picture on the board is that I want to do something without writing too much in terms of definitions, but many of you may be familiar with this construction. There's something you can do with such a poset.
2, 3, 4 is a trouble.
2, 3, 4. Oops, that's trouble. Yes. Horrible. What should it be? 0, 1, 2. No. I mean, these are not independent sets, right? These are flats. It's just a flat. They are flats, so they are not independent. They are the maximal things that contain.
Oh, then there's one edge missing from the other side. 0, 1, 2 is connected to 1 as well.
0, 1, 2 is connected to 1. Thank you. So, yeah. It's not too wrong. It's just a little bit wrong.
Just nice then for the symmetry.
Yeah. Okay. Thank you. These are flats. These are not linear independent sets. So if you start with 2, 3, right? 2, 3 is independent, and then you look at all the vectors in the span of that. That means all the vectors that form a cycle with 2, 3, and that's exactly done. That gives you the flat 2, 3, 4.
I imagine that this motion is not very interesting if the graph is not connected, right?
I think you can do it.
Maybe some direct product of the two.
So there's something you can do, and you probably have seen this before. There's something called the Möbius function for such a set. So the Möbius function is defined so that, and I'm referring to the bottom of the setting here. Möbius function of anti-set is 1, and then the rule is that the sum of the values of the Möbius function across this diagram will have to be 0. That's not very clear, but it will be clear once I do it here. For example, the sum of this and that has to be 0. So these guys get -1 value for this function. Here, the sum of everything that connects the intercept to this has to be 0, and I have 1, -1, -1, so this needs to be 1. Oops. -1, -1, -1 needs to be 2. 1, -1, -1, -1 plus 2 is 0. And exercise that you can do right now. This is what it looks like. This is a little harder to compute, but not really actually, because the sum of everything in the graph should be this diagram should be 0, so 1 minus 5 is -4, plus 8 is 4. Is that no? It's
Negative.
indeed it's -4. Okay, and then the next thing you do, once you've done this, is collect the numbers. So 1 is here, I have -5 over here, I have a total of 8 over here, and -4 over here. I can assemble this information in the polynomial. So for this example, the polynomial will be cubed minus 5t squared plus 8t minus 4. Okay, so
So it's what you call Möbius function. This is really Möbius function in the center of the portion over the center.
yeah, then you
That
write.
polynomial is somehow the analog of the conjecture.
Okay, so there's a gadget, there's a mechanism, and I started with a graph, I obtained this diagonal flats, I did this computation, I got a polynomial for that. There's a function for that. In this example, I should put that here. I'm carrying on this example, but you see what the definition would be in general. This is the characteristic polynomial of the matroid. In this case, would be 3 cubed minus 5t squared plus 8t minus 4. And the reason why I'm bringing this up and I'm trying to cute is that you have another polynomial you can associate with the graph. Very famous polynomial, right? If you start with the graph, you try to color it with t colors. So how many choices you have for this? You can do this in different ways, but I think this is efficient. It's the usual coloring, so you're not allowed to use the same color on adjacent vertices. So you have t choices over here. You have t minus 1 choices over here because you cannot use this color again. The same token, you have t minus 1 choices over here. And now here you have to stay away from these two different colors, so you have t minus 2 choices over here. If you count all of them, you get this called chromatic polynomial.
Why do you have t minus 1 in the bottom? You already chose 2.
Because I'm wrong. The chromatic polynomial is t times all possible choices, t minus 1 is 2 squared. And to expand this, what do you get? So that happens, it's a fact. The characteristic polynomial in this case is t times, sorry, the chromatic polynomial is t times the characteristic polynomial. Okay, so this is what this information captures. If the graph is not connected, you will get just the power of the t corresponding to the number of points. All right, you should be starting to wonder what this has to do with the CSM classes. Remember that for every matroid I can do this. For every matroid I can look at the lattice of flats, and then I can do this operation with Möbius function and get the polynomial of that, and that is the characteristic polynomial. In this case, I can tell you what that means. It is the chromatic polynomial of the type. Is this a new example of matroid? No, because and when we don't get into that, it's very easy to see that every matroid you get out of the graph is in fact realizable over every field, so it's not an example of a new matroid. Okay, so the summary is that matroid capture the asymptotic properties of linear independence. All matroids have a characteristic polynomial, and for realizable matroids, the characteristic polynomial, for graphical matroids, it has this kind of interpretation. Let me give you another way to make a matroid, other in quotes, because it's again an example of realizable, but it will be very relevant to what I want to talk about.
So the realizable ones are always coming from graphs?
No.
Ah, okay.
graphs are they are realizable over every field, so they are regular. And I think they're special. I don't know enough about this.
But you said that the realizable ones had some property for the polynomial. Or not? Maybe
I
was
might
wrong.
have misspoken. The graphical ones have
The ones from the graph. Ah, okay.
but I'll give you, I answer that question. What does the characteristic polynomial mean for a realizable matroid? So the next thing is another example, again, other in quotes, because it's again a realizable example. We start with a hyperplane arrangement. For example, in P. You have any notation, I don't want to actually write this as a bunch of hyperplanes. And let me spill the beans immediately. This is clearly realizable. These HIs are given by the vanishing of some linear functions. Fi are linear polynomials. X0, Xn. So we just view them as vectors in k and plus 1 that is a matroid. A realizable matroid over k. That's not maybe very new, but it's kind of nice to translate what we've seen so far in terms of this information. This is really the same as being realizable. If you give me a set of vectors, I can view them as in the dual space, they can be set of hyperplanes. So there's nothing new in here. And the flats, please remember this, correspond to the intersections of collections. Okay. So that's the dual of taking the span of a bunch of vectors. So here's a question. What is the characteristic polynomial system? Yes. Take your favorite hyperplane arrangement, EPN, construct a matrix this way, and then do this operation, do the Möbius function. What do you get? So there's a small theorem, which is my single contribution to this this, and in fact, better ways to think about the same things were done independently, probably before me by Jude Hub. The CSM class of the complement of the hyperplane arrangement is obtained by replacing T to K. It's a little funny with projective space of dimension K in take the characteristic polynomial. I do not give a name, but this would be the characteristic polynomial. Make a change of variables. The characteristic polynomial, as you realize if you think about how we constructed it, always has a root at 1. It's designed so that if you add these numbers, you get 0. So it has a root at 1. That means it has a factor of t minus 1 after this change of variables. It has a factor of t divided by t. And if you know me, you know I cannot resist to give you an example. So this is an example. Let's be in P2. Take this hyperplane arrangement.
So was it t plus 1 or t minus 1?
T plus 1. And this has a VMT has a root at minus 1. So after this change of variable, it has a root at minus 1. Having a root, in fact, so has a root of 1. Sorry, has a root of 1. So after this change of variable, it has a root of 0.
Yeah.
So for this, again, I'm not going to write all the flats or anything like this, but we can write the basis. The basis of the matroid. Let me just write the basis. They correspond to collection, maximal collections of things that don't intersect. That's what it means. That's the dual notion to explain. So, that's an easy list because there's a total of 4 things, and you just have to see which ones do not intersect. So I have empty intersection 0, 1, and 2. 0, 1, and 2 have empty intersection, right? There's no point coming to 0. And the first 0, 1, 3. 0, 2, 3. The only bad choice is 1, 2, 3. 1, 2, 3 have no empty intersection, so you don't have to do this.
So are you including piloting field?
No, writing P2.
Zero field.
What's the lattice of flats? This is the lattice of flats. Okay, I've done my job correct. These are the flats. 0 and empty set is a flat. Single hyperplanes are flats. These are the flats. They are bases. You want to create the collection. And again, let me do this little game of computing this function. Has to be 1 here, therefore minus 1 here. Such a diagram gives you 1, and this gives you 2. 3 ways to go from 1 to 3 to empty set, and the sum must be 2. And then what's 1 plus 3, 5 minus 4 plus 1. I cannot do these things in real time, but I'm sure that you can do it. Check that that's what you get. So the characteristic polynomial in this case is t cubed minus, what is the sum here? I have 1 minus 4, 5, and minus t cubed minus 4t squared, that's 5t minus 2, and then this factors as t minus 1 squared, t minus 2. This operation that we do just here, for this example, this is equal to t squared, t minus 1, we have a t, so it's t times t minus 1. So the claim is that the CSM class of this hyperplane arrangement, or the complement of the hyperplane arrangement, once you push it forward to Pn, is class of P2 minus class of P1, and if you're good at eyeballing these things, you can check that is the case. Okay. All right. So now the summary again is just seeing what matroids are. We have matroids have a characteristic polynomial, and as I said, this is not restricted. All realizable matroids can be viewed this way, and now I have interpretation for this characteristic polynomial of a realizable matroid up to a mindless operation. It's the same as the Chern-Schwarz-Matthewson class of the complement of the hyperplane arrangement corresponding to the matroid. So this is going in the right direction right now. I'm just seeing why the title is what it is. I've not been thinking about time at all in So I want to spend 1 second on the question of whether all matroids are realizable, and that's the third picture of the board.
Can I ask a question?
Yes, please.
So regardless of matroids, this is very similar to, I guess, the kind of calculations I was hinting to yesterday. And I wonder if you can do this beyond hyperplane arrangements, like arrangement of conics or something.
I have something at some point. I don't know you, but I reached the point where I forget what I've done. I don't remember when and what exactly, but I know I wrote a paper with the title Arrangement of Hypersurfaces. I suppose that I did that. I cannot swear that that is the case. Are all matroids realizable? And the answer is no. look at this. There's a famous theorem, I think it's called Paulus hexagonal theorems. This maybe I could have done in real time, but you start with 2 lines. Start with 2 lines, your favorite lines, and 3 points on the line, 0, 1, 2, and 3, 4, 5. The only reason why I'm drawing this is that this is the datum you start with, and then you do these connections of points in all possible ways, and the theorem is that the 3 points you get in the middle are on the same line, necessarily. So if you can do this, there you go. You get these 3 points are going to be on the same line. How do I get a matroid out of that? I could get a matroid out of the full picture I have over there. Otherwise, how much of this do I want to see? Well, I mean, you can view this in projective space, so these are really secretly vectors in the one-dimensional higher vector space, and then just the matroid corresponding to those vectors. I don't want to spend more than 2 minutes on this, but the point I'm trying to make is very important. That gives a matroid because you know what a realizable matroid is. But the fact is that you can get a matroid by also throwing away.
Sorry, what is that matroid? I didn't get it.
Yeah, we should spend a little more time. So the points 0 to 8 over there are points in projective space. So you will any field, right? You can choose any field. And they correspond to vectors V0, V8. So, for example, do you have any comment here? So the points that is drawn corresponds to rank 1 flats. The lines correspond to rank 2 flats. But I'm not sorry, we know that this is a matroid, it's an aspect of the matroid. The point is that you also get a matroid if you throw away the line 6, 7, 8. So you can get a matroid by all the relations you get over there, but without assuming that 6, 7, 8 are the same. I will not say more about this, but so the theorem, Paulus theorem tells me that if I try to do this in a field, 6, 7, 8 has to be there, but it just so happens that if you throw away 6, 7, 8, you still get a matroid.
So what do you throw away?
So if this is maybe really bad for 6, 7, 8, I mean if
line is the red line.
The red line,
yeah,
right?
Okay. You.
the point I'm making is that this is not realizable. Or anything. So as Richard said that 2,000 years ago, people were thinking about this. Paulus theorem tells you that there are no realizable matroids. Now, is that a pathology or not? And there is a theorem, you can find it. A neat statement is in a paper by Nelson in 2016. Almost all matroids are not realizable. There's a kind of quantified statement. We prove that as n approaches infinity, the proportion of n elements matroid that are representable tends to 0. If matroids are like this, the representable matroids are just. All right, so in fact, the picture I like to advertise is this. We have matroids. And then we have things coming from geometry, right? After all, the complement of a hyperplane arrangement is a geometrical object. So there's a bunch of geometry. Hyperplane arrangements are very special. I should say complement of hyperplane arrangements. They are very special and they correspond precisely to the realizable. Okay, so you have two completely different separate universes. In there you have a very special thing. In the universe of geometry, it's complements of hyperplane arrangement. In the universe of matroids, it's realizable matroids, and they are the same thing in some sense. And this is a bridge to go from combinatorics to geometry or converse. All right, so the natural question at this point is, what's the appropriate generalization of characteristic classes of, I mean, you have CSM classes in this context, so you have CSM classes here. What's the appropriate generalization to the rest?
So this purpose theorem is about when you have, I guess, 6 points and 3 and 3 are in 2 lines. That sounds like something encoded in the matrix. So can you impose some axiom on matrices of some certain size that makes them realizable?
That's a good question. I think no. I think that people try to add actions to the list of matroids.
Apple's axiom.
They may have proven actually that we cannot do that with the concept of actions. People have studied this kind of questions.
But you can realize these things if you extend your notion of what is a field. You have to call things like pastures,
Yes.
hyperfields, things like
Fields,
this.
pastures.
Realizable over a pasture.
So once again, here for this, we have CSM classes. What should they be? Or arbitrary or arbitrary.
First ask, where should they live?
Jörg is, you cannot beat Jörg. That's exactly what we question. Because, you know, if you want to come up with a naive answer, I already gave you a naive answer. In this case, for complements of hyperplane arrangements, you have this characteristic polynomial to say, I have the characteristic polynomial for every matroid, I can take that to be the CSM class. That's what I would have done. And it's not the right answer. There's a much deeper answer. Which is what I want to talk about. All right, let me say that again because I think it's a good point. If you are a naive person like me, you might think that this is the right generalization of CSM classes to arbitrary matroids. Every matroid has a characteristic polynomial. Why don't we take that maybe up to silly transformation to be the CSM class? And the reason is that you have way too much information. You have to think about where this really comes from. You are studying geometrically the complement of a hyperplane arrangement. The classic polynomial captures the CSM class after you plunge it into Pn. But why should you expect that there should be something like Pn for an arbitrary matroid? To make that proposal convincing, you would have to convince me that every matroid has something like Pn stands to the corresponding complement of hyperplane arrangement. Why should there be such a thing? As Jörg says, you have to find the place where the class should live. And you know, I mean, we have known this for a long time. If you have a non-compact variety, where are you going to really look for the information about it? It's kind of an accident that hyperplane arrangements have Pn as a compactification. If I give you the complement of the hyperplane arrangement without telling you it comes from a hyperplane arrangement, that's the open variety. What are you going to do? we're going to try to look for a compact variety which contains that as an open set and such that the complement is a normal crossing divisor. That's where you should look for this information. The natural candidate for a geometric place where this should happen is a compact variety, compactification. Such that the complement is a divisor with normal crossings. The problem with hyperplane arrangements is that's not with PN is that if you need a hyperplane arrangement, the complement of the complement is the hyperplane arrangement. It's not divisor with normal crossings. PN is not the right choice. What is the right choice? Are there better choices? Are there good choices? Are there wonderful choices? Yes, there's the de Concini process is wonderful compactification. So in hindsight, it's clear to me that that is the right choice to make. If there's a canonically defined compact compactification of this open variety such that the complement is divisor with normal crossings. You might think, and this is the kind of things I think and turn out to be wrong, that as soon as you blow up this point, you get a divisor with normal crossing, you could use that. But that's not canonical enough. So even if I start with a hyperplane arrangement that is already in PN satisfying this nice normal crossing condition, this is not, PN is not what I'm going to use. I'm going to use the wonderful compactification, which prescribes that I should blow up all the points and get this alternative picture. These points corresponds to these exceptional divisors. Now this is the wonderful compactification. There's a difference between one and the other. You should keep track of that. I see, of course, if I'm going up nearly as fast as I should. But this is where I wanted to get this point. Okay, so as a first approximation, at least to the question, is for realizable matroids, you should not be thinking of the characteristic polynomial, that is the CSM class in PN. You should be thinking about the CSM class in the wonderful compactification. So as a provisory definition, in the realizable case, I can note that. Let me write it on the board. This is answering your question, your comment. You have to decide where the class should live, and in the realizable case, this is the Nash gap. So, as a preliminary definition, preliminary in the sense that it's only for realizable. So let me just write for realizable. So should they call it cohomology or Chow ring of the people, or Chow group, or whatever? People use the word Chow for this. The Chow ring of a matroid of a realizable matroid M is by definition the Chow ring of the wonderful compactification. Of the corresponding hyperplane arrangement complement. Okay. And the next question is how to generalize that to arbitrary matroids. So you see where I'm going now. This is where the CSM class should live.
So if it's reliable only over finite field, can can still take, we don't have Chern classes, but we can take ad hoc the definition as a CMS class.
This is provisory anyway, so say that maybe I
Okay,
can realize that.
but I'm thinking the opposite. We don't have maybe Chern class in characteristic B, but for the special example, we could give it directly without functionality properties.
Okay, so the first thing is how to do this in general, how to generalize this. It has a big difference. It has a big difference. Are you going to find something that plays precisely the role of the wonderful complication? The answer is no. I don't know whether this cannot be done or it has not been done, but that's not what you do. What you bring in is something you can define for every matroid, and that requires different notation. Every matroid has a Berman factor. Actually, to motivate part of this definition, I had a picture a month ago, but take any example. I had, even in this case, you have to do something to get one quantification. And think of what you do as you do that. If you want to describe the Chow ring of this, well, it will be generated by the classes of these guys. These guys are either proper transformers of these lines or exceptional divisors. In fact, you could even think of the proper transformers of the line as exceptional divisors of the block along them. So it's a bunch of exceptional divisors. And ask yourself, how do I get the class of an exceptional divisor in here? Well, I have to follow his history through blocks. I have to see how I get that exceptional divisor. Maybe I got it on the first stage and then I carried over to the other blocks. Maybe it's one of the last thing I obtained. In general, the one quantification is obtained by blowing up all the flats in order of increasing dimensions. So the class of something here really corresponds to the history that has gone through to get there. That history is a sequence of flats, one inside the other. Maybe that went a little fast, but it will be formalized in this definition. I found it. So let me summarize it, since I have a couple. So the wonderful to get the wonderful compactification, you blow up around all flats in order of increasing dimension. I'm using the word flat for intersection of hyperplanes. Advertise the lattice what the flat is in that case. And classes would correspond to record the history, sequences of flats. We just actually formalize this. To get the Berman fan, you do the following. And its notation, M is a matroid on 0 to n. I consider the real vector space n plus 1 with basis E0 dot En. For some reason, everything will happen in R to the n. Realize that Rn plus 1 modulo the span of 1, 1. We need, so this guy is 0 plus n. And the notation is that for a flat, for actually any subset of 0 n, I would write E sub f as the sum of EI for I in f. Oof, what else? Well, I tried to say this and I didn't write anything because I didn't feel I could write a real good sentence, but again, to understand the classes in here, you have to remember the history that took you there. So a sequence of flags that took you to that particular class, and that is a flag. So I'm going to give F, cursive F, for flags of flags. Okay, so somehow this should know about the child ring or the wonderful multiplication. And then for such a thing, you're going to define a cone. The cone spanned by EF1. That's the vector corresponding to the first flag. Dot EFK. All right. So that gives you collections of cones in array. The Bergman fan is that collection. So we have flags of proper non-empty flags. It hurts my head a little bit to think about this. I have to think about all the flags and then all the flags of flags that are not empty and not the whole thing. For each of them, I will get a cone, and then the Bergman fan is the union case collection. Okay, and then once you have that, I can propose another definition for the Chow ring of M. That is the Chow ring of the toric variety corresponding to this flag, to this
So the size of the torus is n or something like that? What's the dimension of this
yes.
n or m plus or something?
What's the obvious question?
Or n is.
Yeah, do the two. I have a provisory definition that has been erased. In the realizable case, I was proposing the Chow ring of the radical multiplication. Here I'm proposing another Chow ring. Are they compatible or not? Keep in mind that this find is not complete. So this toric variety in general will not be compact. So I tell you that certainly they are not the same thing. Even in the realizable case, this is a non-compact variety, while the one for compactification is compact. But there's a theorem that says that it will work out. I usually see this theorem attributed to Jusvinsky and Fife, the way you're supposed to see it. I had the definition here for realizable matroids. And the theorem is that in the case of realizable matroids, so it's really, I find this a very deep observation.
Can you explain it again?
Yeah, so what happens is that in the realizable case, we have the wonderful compactification. That's a nice compact variety, and it just happens to be inside, that can be put inside the toric variety corresponding to the Bergman family. Don't ask me such difficult questions.
But is there a torus on the reference?
Hmm?
Is Is there a torus on the left hand side?
Right, I don't know the reason for this. So, that's why this thing is deep. I cannot say I understand that this happens. Just take face value that I have the complication realized as a summarizing, and what Zwinsky and Fife prove is that this inclusion.
Hyperplanes that they are like stable. So it's just a combinatorial. I imagine.
This inclusion induces an isomorphism of Java.
So not CSM classes, just where they live.
I'm still just thinking about what they do. All right. And so this is the proposal. Define the Chow ring to be the Chow ring of probability corresponding to delta m, and use Zwinsky and Feichner tell me that for the Reisberg case, I've not changed my definition. And of course, Jean Paul and his four German, three German French classes.
But for the question of tau, so I think you should even look at the dimension. I would guess this is even lower dimension.
This guy is small, but
Yeah, even from the dimension.
yeah,
So that's photo.
that would have to be something else.
Photo is cannot vector.
Yeah, that's okay. So I was going to remind you that for
I mean, you have those acting on a point.
No, the nature of
Compound
tau is
relation.
actually.
So you want this inclusion, so the question is whether this can realize as a T-stable subvariety. As a toric variety, where T is the torus that acts on that toric variety.
Going very little using.
No, I think you cut down.
I was going to mention that you could play the same game for intersection cohomology. You could define the intersection cohomology or something by relying on this man. Jean Paul has written about that, and I believe that people like you are taking your definition, expanding to arbitrary interface and technology. Okay, there's more. I mean, there's much
But
more.
philosophically, we just want to believe that there is a C star action under which the variety, because this the polynomial we are looking after there's just one variable after. So maybe on the ambient space a huge torus X, but the subvariety will be what I expect. It should be just stable under one C star.
Encourage you to look at the literature.
A wonderful communication, because you expect things to be wonderful.
But after all, the chromatic polynomial has a multivariable version.
So there's more to this statement. That's why there's a couple of more things I can say about Chow ring. Number one, this guy has a complete presentation as a quotient of a polynomial ring with variables corresponding to the proper non-empty class. Modulo ideas, which I certainly don't have the time to write down, but these are explicit. Readable. So if you like mechanic 2 and you want to work, or Foscai, suppose, if you want to work in the Chow ring of a matroid, this is what you do. You collect all the proper 90 flats, make a polynomial ring, and then we'll have this idea that gets going. Notation for that, that's another observation. Second observation is that there's a nice presentation for the Chow ring with the toric variety corresponding to a fan, and that goes back to Fulton-Sturmfeld. The elements of A star M, or the Chow ring of M, correspond to Minkowski weights. W or V?
W, right? But pronounced V.
I suppose there's some feeling in that. What are Minkowski weights? These are integer linear combinations of codes. Satisfying the condition, satisfying the so-called balancing condition. Okay, so depending on your point of view, if you are the kind of person you are, you want to work with this, you will do it either in this presentation or by using this. And I see that I'm getting beyond my allotted time. I beg for a few more minutes.
So one question to this picture. So the geometric interpretation of the Jones-Schwarz-Matroid classes in the compactification. We want to translate it to the matroid world and take this abstract homology Chow wave. And this identification is by pulling back, I would guess, so you geometry. So it's not calculating the push forward into the toward variety of the.
As far as I know,
No, it should not be. Okay, it's just to see how they identify.
I should know more about this before we even talk about it. Anyway, we have now a place where the system class should live, and is there a natural CSM class of n as an element of A star n. So what should we get? What we should require? We should require that in the irreducible case, you should get the same as the push forward of the CSM, as the CSM class of the complement in the one-to computation. So if you have that and then you push it forward, you will get the CSM class as a complement of the hyperplane arrangement in Pn, and that will give you the characteristic moment. But this is more refined function that it lives up in the one-to computation, not down. And what else? Well, the minimum you can ask for is that it should satisfy some kind of inclusion-exclusion. That will take it from the irreducible matrix to arbitrary matrix. That's the meaning. The meaning. What's missing here? Counter-right is missing. There's no notion of connection between Chow rings of different matroids, and that part is missing. That for CSM classes that we understand, this is a strong requirement. It should satisfy some kind of inclusion exclusion. Hopefully, if you have this and you're right in the wonderful complication case, that will define the notion of arbitrary matroids.
So you mean by this is what they call this evaluation property?
Yes, value
Okay,
prediction.
that's my understanding. I see it also as a version of motivic nature.
Good. I'm now close to the main point, and for you, close to the end of the talk, which is welcome news, I suppose, but there is such a definition. Can I reproduce it on the board? Not really, because it brings up some information I don't have time to expand on, but this is due to Lopez. Rincon, Fife and Rincon, and Shaw. I think it goes back to 18, so it's been on for a while, maybe 16. Probably was done in 50 years. So let me take the time to write something here. I have a matroid on 0, right? Say that the rank is d plus 1, and I choose 0, k from 0 to d, then they define a k-dimensional CSM cycle, CSM k of n. Yeah, how do we do it? Well, it's the k skeleton with some weight. K skeleton. So I'm taking the point of view here, right? Viewing elements of the ring as Minkowski weights, so as linear combination of cones, the k skeleton with weights, with appropriate weights. And in fact, I can tell you what the weights are. So weights on take a top dimensional cone in the skeleton. remember, the cones are corresponding to flags. So you have to start with the flags of flat. I should tell you what weight you associate with that. Let me tell you if the weight is a sign, -1 d minus k, that's why we need to d on the board. And the product of things that are not told you about. Data of n, funny symbol, vertical line equals I plus 1 slash f of I. So what is this? This is some kind of operation on matroids that corresponds to essentially deletion contraction of graphs. So combinatorial. Let me just write deletion contraction. And that may not even be the right word. Maybe I should write restriction. But there's a simple minded transfer operations for graphs that extends to different things. What is beta? Well, I have to tell you what beta of a matroid is. And beta of a matroid is -1 to the rank of the matroid -1 times, and this will look familiar, the characteristic polynomial with some minus operation. I advertise the characteristic polynomial of any matroid has a factor of k minus 1, to a factor away, then set equals 1, that gives you. That's, I know I'm way out of time, but I want to tell you one more new thing, which is that if you're like me, you don't understand this definition. It is a little bit too combinatorial for me to work with. And it was given in these terms. So the natural question is, can I give it in this terms? Can I give a presentation for that? And there was a conjecture by Rincon and Fife, I believe, for the specific coefficients that would give you that class in here. And here is that, this is why I absolutely want to say this. It's due to two students of mine, there's a theorem. The students are Caraballo-Alba and Jeffery. They prove that the CSM class of a matroid can be written as what they call a stair of n, and you will see what it's called stairs in a moment, but if you write the formula, it will be from 1 to the rank of 1 minus sum over flats, rank flat, at least I, x. Remember, there's a generator in the ring for every flat, it's still up there, so this makes sense. So for example, if n is all subsets of 0, 1, 2, this formula is the following. So all the flats times only these flats. Drop those of lower rank and then drop the last one. And keep the last one for last one. All right, this is something I can understand, and I can plug into a machine and it will tell me. And this implies this explicit formulas that have been conjectured by Fife and Rincon. You realize that one reason why I'm advertising this is that Caraballo-Alba is on the market, and if you want someone who understands the geometry pretty well, and the combinatorics pretty well, and was able to contribute something to the story, then please hire him. If you say you have postdocs, please let me know.
All the application is now running, so it's too late, but now the year to build next year.
What market? Postdoc?
Postdocs. Maybe I should stop here, although, I mean, the obvious...
No one in Minnesota is doing combinatorics.
You would appreciate this. No, this is part, of course, this has been put into a larger story, and there are tautological classes for matroids, and this comes out of that. This was the way it was introduced originally, and that's the newest. Obvious question, do this for other natural classes, other natural classes. One more comment, if you allow me. This is the non-singular story. Complement of hyperplane arrangements are non-singular. From this point of view, matroids are non-singular. Non-singular and open. The compact version was done. The same people have defined, what's it called? Topological. I shouldn't try to remember the terminology. There's a compact version. There's a way to glue these things into something that should behave like a compact object. We have CSM class for that. As far as I know, nobody has approached the singular version. I apologize for this. Thank you so much.
So this upper presentation where you have your formulas. So in my vision, this means it's the analog of the Stanley-Weisner ring if I would work on a compact smooth toric variety or something.
Yes, this is the Stanley-Weisner ring.
But here, of course, we are usually with non-compact toric. But it's similar to the problem we have with these Euler-Malloy type formulas. So we have the geometric player, but that does not mean you need the class and the quotient, but you want to find an explicit formula. This is a choice because you have relations. You want to find an explicit formula in terms of the generators, which in the quotient ring, here in the identification, gives you the class you have geometrically or combinatorially. And that is, of course, from different nature, but it's very similar what we have in the toric situation to do. So we have formulas for characteristic classes, but we have to lift them up into the polynomial ring in the variables to apply them to some applications we want. And that is very descriptive, I think.
I should contact you. I had extremely little, and I'm very proud that they did this work. Right? So, I propose that since after all the class was not down in PM, that it should be in the one application, someone should try to write it geometrically in the one application. And once they did that, they found that they obtained this formula, and then they worked hard to prove that it is valid or satisfies enough division contraction to extend to
There's a phenomenon which doesn't nicely interact with what I'm hearing here, if I understand you. The phenomenon is that if a matrix is realizable, say with a hyperplane arrangement, maybe it can be realized in two very different ways. The moduli space of representations has several components. Actually, the components are different dimensions, and they can be as well as possible. So if you take two realizations, which come from, for example, different dimensional components, then the complements may be very different. And yet, I don't fully understand. I have to hear it another 8 times before I understand. You create something out of it. From both of those, you create the same thing out of it. I'm very confused.
Yeah, that's the first thing. Apparently, that is the case because this depends only on the matrix, doesn't affect the theorization. So I guess theorization will have different one for quantification, but somehow the corresponding system classes in this places there must be relation. Some way to do that. So I guess they will all sit in the toric variety associated with development time in different ways, but evidently the Chow rings are the same and the system classes the same.
I guess there is a notion of morphism of matroids.
I wish I knew what the notion.
Oh,
I keep asking people and I get very different answers.
Okay.
No, I want a morphism matroid which induces a proper, something like proper max, right? Homomorphism of Chow ring. And then I want to go and
Chow
look
ring
at
into a functor and
right, and then hope that
make
these
this
are
class
controllable.
natural in a way or something.
That was my question to my students. I said, we could do that. But they kept running to the roadblock of finding the right class of morphs.
Okay. Maybe I can contribute here. So I think people were interested in the 200 different definitions of matroid because depending on your definition, the notion of morphism is different. Because if you define by rank conditions, then maybe morphism is natural domain. That's different and so on. So, of course, I have nothing to add. I'm just saying that even combinatorially, it's unclear what the morphism should be. It depends on your definition. And the definitions are equivalent, so it's your choice.
I would hope that, that there is an automorphism that produces a map on travelings and then this
But
class
even
is
if you go to the geometric side, you are not in the compact space, we are within the toric space. Takes the child cohomology. So the functionality even there is not the one we are wanting to use for.
That's true, and I glossed over that completely. I mean, the Minkowski weight picture is closer to the homology. Like this is cohomology.
This is homology.
So
Child
probably it would be really in terms very close to what these people do. In terms of weights associated with Minkowski weights. It's a very natural question, and I probably would be an exercise to come up with the right. Frankly, much deeper than I want, actually. Of course, if the universe is built as it should, then this guy will be mathematical.
How would this elementary operation like contraction, restriction, how the showering behaves?
The honest answer is I don't. In fact, I don't even remember what.
No, there is this contraction here.
This guy. Yes. But maybe a hint for that would be looking at the case of graphical matroids. These are really the initial contraction or restriction. I'm sure that question has a very good answer that people have figured out.
Maybe this was in your talk and I missed it, but for realizable matroids, you had a magic correspondence with hyperplane arrangements and this wonderful compactification. And then Chern-Schwarz-McPherson class was the one for this hyperplane arrangement, or the complement is this hyperplane arrangement, right? So I know that in the group in Berlin, and I think also in Frankfurt, people tend to care about the matroid realization spaces. So for a realizable matroid, say realizable over C, there is something called a matroid realization space.
That's what we're supposed to do.
Okay. So the Berlin people are interested in finding smooth bonds and singular bonds, right? And then investigating their singularities. Is there more geometric meaning close to?
If there is any, as Richard was now, this definition only depends on the matroid. So wherever you are on this realization space, so you should have the safe invariants.
I think he looks at for you take one point in the realization space and then look at it, take a microscope, look at it and calculate some CSM test. But there looks at the matrix realization space, which is a several component, very singular space, and you can ask for its CSM test.
I don't know.
I calculated the fundamental tests. And those are like TUT. I don't know how to pronounce TUT polynomial type of data that comes out of the matrix. So the CSM test will be a deformation, one parameter deformation of a TUT polynomial type of invariant of the matrix.
Deformation in which sense?
That the CSM test is a one parameter deformation of the fundamental test. The H bar, which is Jeffery.
You make it into a polynomial by weighting the degrees by homogenization. Then it is a deformation of H. And if you plug in 0, you get the, depending on how you normalize, you get the fundamental space. So T is more as a fundamental space.
Okay.
In this sense.
The top polynomial specializes to the characteristic class.
So there is
Top polynomial is always a key player for all these.
So there is hope that the two CSM classes are related. Actually, in that sense that you are looking, there are two notions.
Yes.
Because you can pick one point in the matrix realization space and take its torus orbit and ask for the CSM class of that. or you can take the whole matroid realization space and take the CSM class. And one is the top polynomial, the other is it's a different, it's a new invariant representative matroid.
So what's the dimension?
The Murphy's law applies. We don't know whatever complication you come up from algebraic geometry, I can come up with a matroid realization space model as that. So even as many components as you want, as many different dimensions as you want.
Okay. So the proposal of defining a CSM class for matroids as in the CSM class of the Resol matroid runs into computational.
Right. So it's like, in my view, it's like singularity. You start at the beginning, but you will never get far away because it's as complicated as anything else in mathematics.
In any case,
It's a theorem by W. Buckley.
But these realization spaces are algebraic vertices over C.
Correct.
So it just means it's not the idea of this kind of singular thing. It's just it's interesting new singular spaces we can try to play our game. So it's a new example of an interesting singular space.
Absolutely.
But I think it's not the idea of what is maybe here to have an intrinsic combinatorial relation.
It looks very different. Yeah.
Okay.
But if both of them have specializations of the task polynomial, some room.
So it would be wonderful if somehow that CSM class itself only depended on combinatorics in a way that doesn't rely on the regular species. If it is really tough.
I suggest to continue this discussions over lunch and after maybe. Let's thank Paolo again.
Thank you for your backup too.